Yeah.
staring at a recipe and thinking, okay, if the butter is soft,
Yeah.
then I can cream it.
Hmm.
Or maybe you're trying to fix your Wi-Fi and you're like, if the light's blinking red, then I need to reset the thing.
Yeah, that sounds familiar.
That kind of everyday, almost unconscious process, applying a rule to what's happening now and then doing something. It's super fundamental to how we get through the day.
It really is.
Welcome to the deep dive.
Huh.
Today we're taking a really fascinating shortcut, actually, into the foundational but, surprisingly relevant world of production systems in AI.
Mm.
Our mission. Let's unpack this complex topic, concept by concept. We want to reveal its kind of surprising history and its critical, often unsung role in shaping the intelligent machines of today and tomorrow.
Yeah, we're going to get into the mechanics, the philosophy, the practical stuff that still matters.
Yep.
At their heart, production systems are, well, they're essentially rule-based systems. They were conceived as a really direct attempt to understand and maybe even replicate human thought processes.
So less about just code, more about how a mind might actually work.
Exactly, decision by decision, in a structured, observable way. Think of them like a sophisticated set of if-then instructions designed to model intelligent behavior.
Okay, and here's the why for you listening in. This isn't just, a dusty computer science history lesson. Understanding production systems. It gives you a fundamental lens, a way to view all AI, from those early expert systems back in the 70s and 80s,
Right.
to today's really cutting edge stuff like large language models. You'll get those first principles insights.
Yeah, you'll grasp how intelligent decisions can be made, how knowledge can be represented, even how those early AI pioneers thought our minds might operate.
It's about seeing the logic underneath all the complexity.
Precisely. And this deep dive, it's based on a pretty comprehensive self-teaching course. So you're getting a structured but hopefully engaging journey through material that, while foundational, is actually making a bit of a comeback now.
A resurgence. Interesting.
Yeah, in today's AI landscape, we're going to peel back the layers, understand the what, the how, and really the enduring why it matters of these systems.
All right, let's unpack it then. To really get production systems, we need to start with the basics, the building blocks. It's one of these things, really.
Okay, well, first off, it's more than just software. Formally, it's an information processing model. It's specifically designed to simulate cognitive tasks.
Cognitive tasks.
Like thinking. Pretty much, the whole idea is rooted in the belief that a lot of human problem solving, our everyday smarts, comes from applying learned rules, those if then things we mentioned, to whatever situation we're in right now. It's a very cognitive centric view.
So it's not just crunching numbers or following steps 1, 2, 3 rigidly. It's trying to copy how we think, how we reason through something. That's actually quite profound.
It is.
Like if you were teaching a robot, a super literal one, to make, say, a PB&J sandwich, you wouldn't just say make sandwich. You'd need incredibly precise if-thens, wouldn't you? Like if bread is on counter and peanut butter jar is open, then scoop peanut butter.
Exactly. Or if a knife has peanut butter and deep bread is on plate, then spread peanut butter. That nails the essence.
So that cognitive centric view, that's the key distinction. Simulating thought, not just coding a function.
That's it. And to do that, every production system has this specific structure, an architectural triad, like a digital blueprint of a mind with specialized parts.
A mini brain. Okay, I like that. With components that mirror how we process info. Let's dive into this triad. First up, the global database, or working memory.
Right. Think of this as the system's mental scratch pad. It's immediate awareness. It holds all the current facts, the data, the things it's actively thinking about right now.
So it's dynamic, always changing.
Very dynamic. Its contents shift constantly as rules fire and new information pops up. So if it's diagnosing a car problem, working memory might hold facts like engine cranks no or lights work yes.
Okay.
It can have temporary notes for the current problem, but also maybe some more permanent background knowledge relevant to cars, like car needs fuel or brakes slow vehicle. It's the system's active present moment.
Got it. Short-term memory, constantly updated. Then there's the knowledge base, also called production memory. This sounds like the long-term storage. where the rules live.
You got it. This is the systems library, its recipe book, the mechanics troubleshooting guide. It's packed with production rules.
The if bends.
Exactly. Each rule is like an independent nugget of knowledge, totally self-contained. If condition, then action. Like if go make cookies, then gather flour, gather sugar, gather butter.
And the power is that they're separate pieces of knowledge.
Precisely. Each rule is its own distinct piece of expertise.
And each rule has two parts, right?
Mm.
LHS and RHS, left-hand side, right-hand side.
That's right. The LHS, the left-hand side, is the IF part, the conditions. It specifies what pattern of facts must be sitting in working memory for this rule to even be considered. It's the trigger.
Okay.
The RHS, the right-hand side, is the then part, the actions. It says what the system does if the LHS conditions are met. Usually this means messing with working memory, adding new facts, maybe removing old ones, or changing something that's already there. It's the consequence.
And the beauty of this, thinking about building and fixing these things, is the modularity. You said each rule is independent.
Yeah.
So you can add a new recipe to grandma's book without rewriting the whole thing. Or tweak one card diagnostic rule without breaking 10 others.
That's exactly the advantage. It makes these systems scalable, maintainable. You avoid that house of cards effect you get in other kinds of programming.
Makes sense.
Yeah.
Okay, so working memory, scratchpad, knowledge base, rulebook. What's the third part of the triad?
That's the control system, but it's usually called the inference engine. This is the active bit, the orchestrator, the brain's conductor, maybe?
The part that actually does the thinking.
Sort of, yeah. It manages the whole show, the interaction between the knowledge base, the rules, and the working memory, the facts. It runs the core loop, the recognize act cycle.
Recognize act cycle.
Okay.
And its job, if we break it down to first principles, is threefold. One, match. It's constantly comparing all the rule conditions, LHS, against the current facts in working memory. Finds all the rules that could apply right now.
Okay. Finds all possibilities.
Two, select. Now, if multiple rules mash, and that happens a lot, it has to choose just one rule to actually execute. This is where that conflict arises, and we'll get into how it chooses later. It's a critical step.
Makes sense. You can only do one thing at a time.
Right. And three, execute. It fires the chosen rule, performs the action, RHS, which updates the working memory, and then the cycle starts right over again. Match, select, execute, constantly.
So that loop match, select, execute, that's the engine's heartbeat. It drives the system forward from whatever state it's in towards some goal. Can you walk us through that loop again step by step just to really cement it? Absolutely. Think of it as this continuous dynamic process, the engine of reasoning. Step one, match. Also called recognize. The inference engine meticulously scans all the facts currently in working memory. It checks every single rule in the knowledge base to see which ones have their IF conditions met by those facts.
Like checking every book on the shelf against a keyword.
Exactly. All the rules that are satisfied get tossed into a temporary bucket called the conflict set.
Conflict set, okay.
Yeah.
Like all the kids raising their hands because they know the answer.
Perfect analogy. They all have a valid potential response based on the current situation. Step two, select. This is conflict resolution, the decision point. Now, if that conflict set is empty, no rules matched, no hands raised, the system just stops.
Yeah.
Nothing more it can do with its current knowledge.
Makes sense.
If there's only one rule in the set, easy choice, that one gets picked. But if there are multiple rules, the system has a conflict. It then uses a specific predefined conflict resolution strategy to pick the winner. Which rule gets priority? That strategy is key to how the system behaves.
We'll definitely need to unpack those strategies later.
We will. Step three, execute or act. The chosen rule fires. Its then action is performed. Almost always, this means changing working memory, adding a new fact, deleting an old one, modifying something, like asserting car status battery dead, or goal achieved sandwich made.
And then the cycle repeats immediately.
Instantly. Working memory is updated, so back to step one, match. See what rules apply now in this slightly different state? It's this constant loop that lets the system adapt, react, and hopefully make progress towards its goal.
And it just keeps going until
Uh,
until a goal is met or it runs out of rules to fire.
Exactly. Either it reaches a state defined as success, or it reaches a state where no rule conditions are met in working memory. It's a beautifully adaptive process.
It really clicks when you break it down like that. Okay, so beyond this core cycle, what are the other big characteristics that make these systems, as you said, powerful and transparent?
Right. Their enduring value comes down to a few key things. First, simplicity and transparency. That if then structure. It directly mirrors how we naturally think about conditional logic. If this, then that.
Makes it easy to understand.
Incredibly easy for humans to read, trace the reasoning, verify why a decision was made step by step. This is huge compared to, say, modern black box AI, where understanding the why can be almost impossible.
Right, the opacity problem.
Exactly. Second, modularity. We touched on this. Knowledge is in these discrete, independent rules. Adding a new rule, fixing one, deleting one usually doesn't break the whole system, makes development and maintenance much, much easier, like adding pages to a loose leaf binder.
Scalable.
Very. Third, knowledge intensive. The system's smarts come from the rules themselves, not from some super complex algorithm in the inference engine. The engine is pretty generic. The knowledge is specific.
You can swap out the rule book for a different topic.
Absolutely. Use the same engine for medical diagnosis, financial advice, or car repair just by changing the knowledge base. Highly adaptable. And finally, flexibility and interruptibility. Unlike a traditional program that follows a rigid script, a production system is data driven. What it does next depends entirely on what's in working memory right now.
So it can react
Instantly. If new important info appears or the environment changes, it can immediately shift focus. It's not stuck finishing step 7 if step 3 just became invalid. Makes them great for dynamic situations.
Okay, architecture, check.
Correct.
Heartbeat cycle, check. Characteristics, check. Now, how does this digital brain actually reason? Because, we don't just think one way. Sometimes we work forward from clues, sometimes backward from a goal.
You're absolutely right. And the inference engine reflects that. It's not a one trick pony. It has two main strategies, two different ways of thinking that fundamentally change how it tackles a problem: forward chaining and backward chaining.
Forward chaining first. Starts with known facts, applies rules to derive new conclusions.
Yeah.
Sounds like detective work, gathering clues, seeing what story emerges.
That's a great analogy. It's a classic data driven approach, sometimes called bottom up reasoning. You start with the initial facts you have in working memory.
The observations.
Right. The system then cycles through its rules, finds any whose IF parts match those facts, and fires one. That action usually adds new facts to working memory.
Which might trigger other rules.
Exactly.
Yeah.
Creates a chain reaction. New facts trigger more rules, which add more facts, and so on. It's like the detective collecting every single clue, putting them on the board, and seeing what connections, what overall picture emerges naturally. You're following the data trail wherever it leads.
Could you give an example?
Sure. DENDRAL, one of those early, really successful expert systems, its job was figuring out chemical structures from mass spectrometry data.
Yep.
It started with the raw data, readings the facts, and applied its chemistry rules to figure out all the possible molecular structures that could fit that data. It was exploring possibilities based on the evidence.
So it's exploratory, not aiming for one specific answer from the get go, just seeing what you can deduce from the incoming data. Seems useful for planning or monitoring systems, reacting to live info.
Precisely. Planning real time monitoring, process control situations where you need to react to what's happening. Now, the other side of the coin is backward chaining. This is goal driven, top down reasoning.
This sounds more like a doctor diagnosing. You have a hunch, I suspect it's X.
Mm-hmm.
And then you work backward to find the evidence to confirm or deny it.
Perfect analogy. It's heavily used in diagnostic systems for that reason. The system starts with a specific goal, a hypothesis it wants to prove, or maybe a question it needs to answer.
Does the patient have meningitis?
Exactly. Then it searches the knowledge base for rules whose action, the then part, would achieve that goal.
Okay.
Once it finds such a rule, the conditions of that rule, the IF part, become new sub-goals, things it now needs to prove.
So it breaks the problem down.
Recursively. It keeps working backward, turning the main goal into a chain of smaller sub-goals until it hits sub-goals that are either already known facts in working memory or things it can directly ask the user about.
Like MYCIN, the medical system. You said it did this.
Masterfully. It would start with a possible diagnosis, then work backward, asking the doctor very specific questions. Does the patient have a fever? What did the lab results show for X? But only the questions needed to confirm or rule out that initial hypothesis. Very targeted.
So backward chaining is super efficient if you know what you're looking for. It really shows how you need different strategies for different problems. Can we maybe compare them side by side?
Absolutely. Laying them out really clarifies their strengths. Starting point. Forward starts with facts, derives conclusions. Backward starts with a goal, seeks facts, direction. Forward is data driven, bottom up. Backward is goal driven, top down. Search. Forward tends to be broader, exploring all consequences. Backward is often deeper, pursuing one line of reasoning, depth first. Objective. Forward finds all possible outcomes. Backward confirms, denies one specific outcome. Analogy. Forward is following a recipe step by step. Backward is figuring out what ingredients you need if you want to bake a cake. Uses. Forward shines in monitoring, planning, control. Backward is great for diagnostics, troubleshooting, advice, efficiency. Forward can be inefficient if the goal is known, explores too much. Backward is efficient for specific goals, focused inquiry.
That comparison is a real aha moment. You pick the tool for the job. But what happens back in that match phase? When multiple rules do match, you said the system forms a conflict set. How does it pick just one winner? Who goes first?
That's where the conflict resolution strategy becomes absolutely critical. You've got the set of rules, all applicable, all potentially valid actions to take right now. The system needs a clear, consistent way to choose just one.
Like the teacher picking which kid with their hand up gets to speak next.
Exactly. That strategy is the system's attentional policy. What does it prioritize when faced with multiple options? This choice dramatically affects behavior.
So it dictates what the system pays attention to. What are some of the classic strategies? The foundational ones.
There are several well established ones. Specificity. This one favors the rule with the most detailed conditions. The thinking is a rule matching a more specific situation is like a special case and should probably override a more general rule.
More conditions met or more specific.
Right. If one rule says AF, car is red, and another says IF, car is red, A and D has flat tire, the second one wins if both are true because it's more specific to the current situation. Favors precision, recency. This strategy prefers rules that match the newest facts added to working memory. The assumption is that recent information is probably more relevant to what's happening now, makes the system responsive.
So if I just told it the door opened, rules about open doors get a boost.
Exactly. Keeps the focus on the latest developments, priority, or salience. Here, the developer just assigns a fixed priority number to each rule when they write it. Higher number wins. Simple, gives direct control, but it's static, doesn't adapt to the situation.
Like a fixed checklist order.
Sort of, yeah. Arbitrary choice. The simplest, but usually the worst. Just pick one at random from the conflict set. It ensures something happens, but makes the system unpredictable. Hard to debug, hard to trust. Imagine your car's diagnostic system just guessing.
Yeah, okay, arbitrary seems like a bad idea for anything serious. Are there more advanced strategies, maybe combining these or adding other smarts?
Oh, absolutely. Real world systems often get more sophisticated. Refractoriness. This one is super important, maybe the most important, for preventing infinite loops. Simple idea. A rule instance, a specific rule matching a specific set of facts, won't fire again on the exact same facts until at least one of those facts changes.
So we can't just keep doing the same thing over and over if nothing changes.
Exactly. It prevents getting stuck asking, is the door open? Repeatedly when you already said yes and nothing else happened. Ensures progress. It forces the system to wait for new information or a state change. Combined strategies. Many systems use a hierarchy. Maybe they apply recency first to filter the conflict set. If there's still a tie, then they apply specificity to pick the final winner. Or specificity, then recency. This gives you a nice balanced responsive, but also favors more detailed knowledge. It allows for more nuanced control over the system's focus.
Layering the strategies. Clever. Okay, so we've got how they reason and resolve conflicts. But you also mentioned production systems can be classified by the formal properties of their rules. This determines the physics of the problem space they work in.
Exactly right. Understanding these formal properties helps you match the system type to the problem type. It reveals the underlying assumptions the system makes about the world it's modeling.
Monotonic versus non-monotonic. A monotonic system is one where facts are only ever added. Once something is true, it stays true forever. Conclusions are permanent, irrevocable.
Like a mathematical proof. Once proven, it's done.
Perfect example. Or maybe a simple calculation. Once you add 2 plus 2 plus 2 is 4, that fact doesn't get retracted later. Good for static domains where knowledge doesn't change. But most real-world situations aren't like that, right? So we have non-monotonic systems. These are much more common and frankly more useful for complex problems. Here, facts can be retracted or changed.
So the system can change its mind or update its beliefs.
Exactly. Previous conclusions can be invalidated if new information comes along.
Yeah.
Think about a robot navigating a room. It might believe the path ahead is clear, fact. Then a sensor detects an obstacle. It has to retract the path clear, fact, and update its internal state. This ability to handle incomplete or changing information, to revise beliefs, is crucial for dealing with the real world.
Definitely sounds more flexible, more realistic. Okay, what about commutative and partially commutative systems? Sounds like it's about the order of things.
It is. It deals with whether the sequence in which rules fire affects the final outcome. A commutative system is one where the order of rule application makes absolutely no difference. Any valid sequence of rules leads to the exact same final state in working memory.
Like doing independent chores. Doesn't matter if you wash dishes then vacuum or vacuum then wash dishes, the end result is the same.
Precisely. This simplifies the control strategy immensely because you don't need to worry about sequencing. More common is a partially commutative system. Here, for some rules, order doesn't matter, but for others, it's critical. It's a mix.
Like cooking. Chopping veggies and boiling water can happen in any order relative to each other, but you have to boil the water before you cook the pasta.
Excellent analogy.
Hmm.
Some steps are independent, others have dependencies. Most complex problems have this mix. Understanding this helps designers manage the reasoning flow effectively.
That makes total sense. Okay, we've really nailed the mechanics, the reasoning modes, the underlying physics. Let's jump in the time machine now, because production systems are tied right into the birth of AI itself. This is the AI origin story, isn't it?
It absolutely is. The intellectual DNA of production systems comes directly from the dawn of AI as a field. We're talking about pioneers Alan Newell and Herbert A. Simon back in the 1950s at Carnegie Mellon.
Right.
They had this radical belief that human problem solving, the very essence of intelligence, could be understood, formalized, and ultimately replicated as information processing. They were asking, fundamentally, can thinking be computed?
And they built the logic theorist in 1956, one of the very first AI programs. Groundbreaking stuff. It could actually prove mathematical theorems, a real demonstration of machine intelligence.
It was huge. And that work led to one of the most influential and controversial claims in AI history, the physical symbol system hypothesis, or PSSH.
PSSH. Okay, sounds important. A physical symbol system has the necessary and sufficient means for general intelligent action. Whoa.
Yeah, unpack that. Necessary and sufficient.
So they were saying intelligence isn't some magic spark, not just biological. It can emerge from any system as long as it can manipulate symbols according to rules. That's bold for the 50s.
Incredibly bold, paradigm shifting. It fundamentally challenged how people thought about minds and machines.
Mhm.
The PSSH makes two huge claims.
Anything generally intelligent, like us, must be a physical symbol system underneath. It has to work by manipulating symbols.
Any physical symbol system, if you set it up right, can be made generally intelligent.
So thinking is computation, essentially. Intelligence is an emergent property of symbol manipulation.
That was the core claim, not tied to biology, but to the logical structure of processing symbols according to rules. This idea laid the philosophical and practical foundation for all of symbolic AI, the dominant approach for decades.
And looking back at our architectural triad, production systems are physical symbol systems, right? Working memory holds the symbols, the knowledge base has the rules for manipulating them, and the inference engine is the processor doing the manipulation.
You've got it. They are the direct embodiment of the PSSH,
Hmm.
a concrete way to build systems based on that hypothesis.
And this theoretical framework didn't just stay theoretical, it led directly to the golden age of expert systems in the 80s, didn't it? That AI boom.
It absolutely did. The PSSH gave people a blueprint. Expert systems were the practical application.
Mm.
Capture human expertise in a narrow field and automate the problem solving. Put an expert's reasoning into a box. Two early examples really stood out.
Let's hit DENDRAL first, the 1960s chemical detective.
Right, developed at Stanford, Feigenbaum, Buchanan, Lederberg. Its job? Help chemists identify unknown molecular structures from mass spectrometry data.
A seriously complex, real world scientific problem.
Totally. Dendral had a huge knowledge-based chemistry rules, but also expert heuristics, those practical rules of thumb that experienced chemists use. It worked with a plan-generate test cycle. Propose possible structures, then use its rules to prune away the impossible or unlikely ones.
And its legacy.
It proved AI could tackle genuinely hard scientific problems, not just toy examples, and deliver real value. Big.
Huge. Okay, then maybe the most famous one, MYCIN, 1970s, the medical maverick.
Also Stanford. MYCIN aimed to help doctors diagnose infectious blood diseases and recommend antibiotics. Classic production system. Over 600 rules painstakingly gathered from top medical experts.
And it used backward chaining, like we discussed. starting with a possible diagnosis.
Exactly. Could it be bacterial meningitis?
Yeah.
And it will work backward, asking the doctor specific relevant questions based on its rules to confirm or deny that hypothesis. Super targeted questioning.
But MYCIN had that killer feature, the one that feels so modern now, explainability. You can tell you why.
That was its superpower and a crucial insight. It could answer, why are you asking me this question? Or how did you reach that recommendation?
How did it do that?
It would just show the rule it was currently trying to satisfy. I'm asking about X because I'm trying to confirm condition Y in Rule 257, which suggests diagnosis Z. This transparency was revolutionary for building trust. Doctors could follow the logic, not just get a black box answer.
That's a direct line to modern explainable AI, XAI, isn't it? The need to understand why an AI makes a decision.
Absolutely.
Uh,
MYCIN is a direct intellectual ancestor. Even though it wasn't widely deployed in hospitals, there were ethical questions, integration issues.
right, who's ultimately responsible?
Exactly. But its performance often matched or beat human experts in its narrow field, and it massively influenced AI design.
Yeah.
It showed the potential for trustworthy AI way ahead of its time.
Incredible successes. But despite systems like DENDRAL and MYCIN, the bloom came off the rose, cracks appeared, the infamous AI winter arrived. What went wrong? What were the big critiques, both philosophical and practical?
Both fronts were significant. Philosophically, the biggest bombshell was John Searle's Chinese room argument in 1980. It was a direct attack on strong AI. The idea that a sufficiently complex program doesn't just simulate understanding, but actually has understanding, consciousness, a mind.
The Chinese room. Always a fun one to think about. So the setup is I'm locked in a room. I don't speak a word of Chinese.
Yeah.
People slide Chinese characters under the door. But I have this massive rule book, all in English. It says, if you see this squiggle, write down that squiggle. I follow the rules, manipulate the symbols, pass the results back out from outside. Looks like fluent Chinese conversation.
Looks perfect. But Searle's point is, you inside the room never understand a single word of Chinese. You're just shuffling symbols based on rules, syntax, without any grasp of their meaning, semantics.
Just following instructions.
Exactly. And Searle argued that's all a digital computer does. It manipulates symbols according to its program, but it has no genuine understanding, no consciousness, no intentionality. It's a syntax engine, not a semantic engine. It doesn't get it.
Which directly challenges the PSSH, especially the sufficient part. Simple manipulation alone isn't enough for intelligence.
That was Searle's powerful argument. It really forced the field to grapple with what understanding truly means for a machine. Now, there are counter arguments. Maybe the whole system, room, person, rules, understands, even if the person doesn't. But it was a major philosophical challenge.
A big conceptual hurdle, but there were also very real down to earth problems that hit hard, leading to the AI winter, right? Practical roadblocks.
Oh, absolutely. Huge ones.
The knowledge acquisition bottleneck. Expert systems lived or died by their rules, but getting that knowledge out of human experts.
The ones who often can't even explain how they know what they know.
Exactly. Extracting that deep, often implicit expertise and painstakingly translating it into formal IF-then rules, that whole knowledge engineering process. It was incredibly slow, difficult, expensive, and prone to errors. It just didn't scale. This was probably the single biggest practical barrier, like trying to bottle lightning.
Okay, getting the knowledge in was hard. What else?
Then there were fundamental issues with brittleness and scalability. Brittleness. These systems were amazing within their very narrow domain. MYCIN knew blood infections, but just slightly outside that, they fell apart completely. They had no common sense, no ability to handle unexpected input gracefully. If MYCIN saw a patient with a broken leg, it would be utterly clueless. Brilliant, but fragile. Scalability. As you tried to add more and more rules, going from hundreds to thousands, the system became this tangled mess. Adding one new rule could have totally unforeseen, disastrous side effects, interacting weirdly with rules written years ago. Debugging became a nightmare. It just didn't scale gracefully.
So deep philosophical doubts combined with these really painful practical limits, difficulty getting knowledge in, fragility, scaling issues, it all led to disillusionment. Funding dried up.
Exactly. The hype bubble burst. People got skeptical. This was the AI winter. And it really cleared the path for connectionist approaches, neural networks to gain traction later as an alternative way forward.
The symbolic approach hit a wall. But as you said, the story didn't end there. Challenges often spark innovation. And Module 4 is about the engineering, particularly one key breakthrough that made these systems even possible on a larger scale.
Right. Without this, expert systems might have remained small academic toys.
The Rete algorithm. The secret sauce for making rules run fast. What was the problem it was solving? Why were early systems slow?
The core problem was computational cost. Imagine a system with thousands of rules and hundreds of facts in working memory. The naive approach is on every single cycle, check the conditions of every rule against every fact.
That sounds incredibly inefficient. Like rereading the entire library catalog every time one book is added.
Exactly. Computationally intractable for anything non trivial. It just wouldn't scale. Charles Forgy at CMU came up with the Rete algorithm, pronounced Rete or Rete, in 1974 to solve this.
A fundamental optimization, then. A first principle of efficient AI processing. How did Rete work its magic?
It's really elegant. Instead of reevaluating everything from scratch on each cycle, Rete does something clever. It compiles all the rule conditions from the knowledge base into a specialized data structure, a network. Think of it like a decision tree or a graph optimized for matching.
Okay, precompiles the rules into a network.
Right. Now, when a fact is added or removed from working memory, that change propagates through this network. The network efficiently figures out only which rule matches have been affected by that specific change. It avoids redundant checks by exploiting two key ideas. One, temporal redundancy. Working memory usually changes only slightly from one cycle to the next. Reta remembers the results of matches from the previous cycle. It maintains state in the network and only calculates the differences caused by the new changes. It processes the delta, not the whole state. Two, structural similarity, sharing. Different rules often share parts of their conditions, like maybe 20 rules all need to check if status emergency. Rita builds the network so that this shared test is done only once and the result is shared among all rules that need it. This happens in what are called alpha nodes, testing single facts, and beta nodes, testing combinations of facts within the REIT network structure.
So it remembers previous work and shares common tests, like an optimized workflow.
Exactly. Think of that optimized post office again. It doesn't resort everything daily. It has routes, the network. New mail, fax, flows through, gets sufficiently directed only where needed based on the address conditions, using shared routes for common destinations. REIT made large scale production systems computationally feasible, a massive breakthrough.
Huge leap. And building on that efficiency, we got expert system shells, the developer's toolkit, making it easier to actually build these things.
Precisely. Once you have an efficient engine, like one based on rate, you can package it up. An expert system shell provides the core infrastructure, the
Right.
inference engine, the working memory structure, the knowledge base framework.
So developers don't have to reinvent the wheel every time.
Right. They, or even domain experts, can focus on the hard part, the knowledge engineering, writing the actual if then rules for their specific problem without building the underlying AI engine from scratch.
Democratizing the tech, basically.
Yeah.
Moving it out of pure research labs.
Yeah, and you saw an evolution. Early ones like OPS5 were often in Lisp. Then came CLPS, C Language Integrated Production System from NASA. Big deal because it was public domain, easy to integrate with C code, still used a lot.
CLAPS.
And then JSS, Java Expert System Shell, tightly integrated with Java, very popular for enterprise applications. JESS also added features like backward chaining, making shells more versatile. This evolution mirrored AI becoming more integrated into mainstream software development.
Following the trends in programming languages. Love it.
Ooh.
Speaking of practical, you mentioned a capstone project, building a car mechanic in code. Let's make this concrete.
Yeah, let's illustrate how you'd build a simple diagnostic system using something like CLPS. We'll focus on common, relatable problems. Car won't start, and engine misfire makes the abstract ideas tangible.
Okay. Step one is always that tough part. Knowledge engineering. Talking to the mechanic, getting their diagnostic logic.
That's the core. You sit down with an expert mechanic, watch them work, look at their manuals. How do they troubleshoot won't start? Maybe they ask, engine cranks? No. Lights work? No. Diagnosis, dead battery. If lights do work but no crank, diagnosis, bad starter, you capture that decision tree.
And that tree becomes the blueprint for the rules.
Exactly.
So how does that look in C-Clips? Can you give us a taste of the code?
Sure. First, you define how you'll represent facts, like symptoms, maybe a div template clips, div template symptom, slot name, slot value.
Okay, a template for symptoms.
Then you can assert facts into working memory, like symptom, name engine cranks, value no, or symptom, name lights work, value yes.
Got it. Facts represent the current situation. Now the rules.
Rules use defrule. A simple diagnostic rule might be CLIPS, defrule diagnose dead battery, symptom, name engine cranks, value no. Condition 1, symptom, name lights work, value no. Condition 2, then action, assert diagnosis likely a dead battery. Add diagnosis fact, print out diagnosis, check the battery, Tell the user.
So if engine doesn't crank and the lights don't work, then assert dead battery and tell the user. Straightforward, if then.
Exactly. The engine matches facts on the left, LHS, and performs actions on the right, RHS.
But how does it get those initial facts? How does it know to ask me if the engine cranks? That requires managing a conversation.
Good question. You use dialogue management rules. You write rules that check if a needed piece of info is missing. For example, a rule might check, is there any fact about engine cranks yet? If not, its action is to ask the user.
How does it ask?
It uses printout to, is the engine cranking? Yes, no. To display the question, then read to get the user's input, and finally assert to put the answer, like symptom name engine cranks value, yes, into working memory.
So asking questions is just another rule firing based on missing information. And that new information then potentially triggers the diagnostic rule?
Precisely. It drives the reasoning forward.
And you mentioned using control facts to manage the flow, to make sure it asks questions before diagnosing. That sounds like a neat trick for ordering things in a system that's fundamentally reactive.
It's a standard and really effective design pattern. You use special facts just for control, like phase welcome, or phase ask questions, or phase diagnose.
Okay.
Rules for a specific phase will require the corresponding control fact on their LHS. So a question asking rule might need phase ask questions to be present before it can fire. When all questions in that phase are answered, a special rule fires that retracts phase ask questions and asserts phase diagnose.
Switching the system's focus to the next stage.
Exactly. It imposes a logical sequence on the interaction, guiding the user through steps, even though the underlying engine is just reacting to whatever facts are currently true. It brings order to the data-driven chaos, if you like.
That example really pulls it all together. It shows how you break down complex problem solving, like diagnosing a car, into these transparent, logical, rule based steps. You can literally read the rules and see the experts thinking.
And that transparency, that ability to see the why, is becoming incredibly important again, especially when we look at modern AI.
Perfect transition. We've covered the history, the mechanics, the engineering,
Mm.
but the AI world today looks very different, often dominated by other approaches. What's the great divide, and where do production systems fit in now?
Yeah, the AI landscape, especially since the 80s, has often felt like a tale of two paradigms, constantly interacting, sometimes competing. Symbolic AI versus connectionist AI.
Symbolic AI, that's our production systems. Joe FAI, good old fashioned AI.
Yeah.
Explicit rules, logic, structured knowledge.
Exactly. Rooted in the PSSH, believing intelligence comes from manipulating symbols according to rules. Great for structured tasks, logic, explanation, but we saw its limits. Brittleness, the knowledge bottleneck, that led to the AI winter.
And the other side, connectionism, neural networks, machine learning, deep learning. This is what most people think of as AI today, right?
It's definitely captured the spotlight. Inspired by the brain neurons, connections. Instead of explicit rules, these models learn patterns implicitly from massive amounts of data. They tune connection weights.
And they're incredibly good at certain things.
Phenomenal success in perception, image recognition, speech. Tasks where writing explicit rules is basically impossible, but their big drawback is opacity, the black box problem.
They work, but we often don't know why.
Exactly. It's hard to understand their internal reasoning. Why did it classify this image as a cat or that transaction as fraud? Often inscrutable.
So, explicit, transparent logic versus implicit, powerful, but opaque pattern recognition. And the limits of both are now leading to a middle ground, a hybrid approach.
Precisely. There's a growing sense that neither side alone is enough for robust general intelligence. This is driving the rise of neuro-symbolic AI.
Neuro-symbolic, combine the two.
The goal is to get the best of both worlds. Blend the learning power of neural nets with the transparency, logic, and reasoning of symbolic systems like production systems. And those production systems, they're staging a comeback as key components here, precisely because they're explainable.
So, how do you actually combine these fundamentally different approaches? What do these hybrid architectures look like?
There are several really interesting ways they're being integrated. Henry Kopps laid out a useful taxonomy. Symbolic neural. Here, a high-level symbolic system, like a planner or a production system, runs the show. But when it needs complex pattern recognition or intuition, it calls a neural network as a subroutine.
Like AlphaGo, symbolic search guided by neural net evaluations.
Perfect example. The symbolic part does the strategic thinking. The neural part provides the gut feeling about board positions. Logic directs intuition. Neural calls symbolic. This is getting really common, especially with LLMs. A neural model good at language, maybe generating ideas, learns when it needs precise logic or verified facts. So it learns to call out to an external symbolic tool.
Like an LLM asking a calculator for math, or a rule-based system for a specific fact or compliance check.
Exactly. The neural net handles the fuzzy stuff. The symbolic tool handles the precise, verifiable stuff, augments the LLM's weaknesses. Deep learning plus rule-based systems. This is super practical, especially in industry, often a two-stage process. First, a deep learning model does heavy pattern recognition, finds defects on an assembly line from images, flags anomalies in medical scans, spots weird financial activity.
Handles the complex perception.
Right. Then the output of that neural net, potential defect found, transaction flagged, is fed into a production system. This system applies explicit business rules, domain constraints, regulations.
To make the final explainable decision.
Exactly. Yes, this is a critical defect according to rule X, or this transaction violates regulation Y. You get the power of deep learning plus the clarity and auditability of rules.
That makes so much sense. But wait, if the knowledge engineering was the big bottleneck before, how do you get the rules for that second stage now? Still seems hard.
That's where another crucial development comes in. Learning production rules from data. This directly tackles that old bottleneck. Instead of a human painfully writing every rule,
The AI learns the rules itself.
pretty much, algorithms can now induce if then rules directly from datasets. Think of decision trees. A trained decision tree is essentially a set of if then rules you can read directly. Other techniques like sequential covering or Bayesian rule lists can also automatically discover interpretable rules hidden in data.
Whoa. So you get the learning power of modern ML and the transparent structure of rules.
That's the goal. It bridges the gap.
And this connects directly to explainable AI, XAI, that critical need for trust, especially in high stakes areas.
Absolutely critical. Healthcare, finance, autonomous driving. You can't just have a black box making life or death decisions. You need justification. You need audit trails. XAI is all about meeting that need. And production systems, being inherently transparent with their readable rules, are a natural fit, a powerful tool for XAI.
So their big value now isn't just solving problems, but making other AI systems understandable and trustworthy.
That's a huge part of their resurgence. A common XAI pattern uses a rule-based system as an explanatory layer or maybe a guardrail for a neural network.
How does that work?
Okay, deep learning model flags a transaction as potentially fraudulent. Instead of just outputting fraud risk 95%, it passes details to a rule-based system. That system checks its explicit rules, e.g. company policy, regulations, and explains. Flagged because amount $10,000 in deed destination is high risk country violating rule 7.2.
So you get a clear, logical reason tied to a specific policy or rule.
Exactly. Auditable, understandable, builds trust. It makes the overall system far more accountable.
That's incredibly valuable. As AI gets everywhere, that trust and accountability is non-negotiable. Okay, what about the absolute cutting edge, the future? How do production systems interact with large language models, LLMs? They seem to be rewriting the AI playbook.
LLMs definitely complicate the picture. They're connectionists at their core, trained on vast text data, but their ability to manipulate language, which is symbolic, blurs those old lines.
Yeah, it's a hot debate, right? Are LLMs showing some kind of emergent symbolic reasoning? Or are they just incredibly sophisticated parrots, great at mimicking patterns without real understanding? People like Jan LeCun seem skeptical about their deep reasoning abilities.
It's a critical discussion, but regardless of how LLMs internally work, the most promising path forward for truly capable and trustworthy AI seems to be integrating them deeply with symbolic engines like production systems.
A hybrid future again, best of both worlds. How would that synergy work?
Think about their complementary strengths. The LLM is amazing at the fuzzy front end, understanding natural language prompts, extracting knowledge from messy text, maybe even generating potential rules or hypotheses.
Okay, it handles the interface, maybe the initial knowledge extraction, overcoming that old bottleneck.
Potentially, yes. Then, that output, the structured info, the potential rules, gets fed into a symbolic engine, a production system. The production system provides the rigorous, verifiable, step by step logical reasoning. It checks for consistency, applies constraints, executes complex plans reliably.
So the LLM provides the broad knowledge and intuition, and the production system provides the discipline, logic, and fact checking, overcoming the LLM's weaknesses in consistency and truthfulness.
That's the symbiotic vision. The LLM makes knowledge acquisition easier. The PS makes reasoning more reliable and transparent. It's not about replacement, it's about empowerment. Production systems aren't dead history, they're becoming crucial partners for the next generation of AI.
Fascinating. It's amazing how these ideas cycle and recombine. But production systems aren't just about practical AI applications. They're also at the heart of ambitious projects trying to model the human mind itself. Cognitive architectures, trying to build a unified theory of thinking.
Exactly. This takes us beyond expert systems into the realm of cognitive architectures. These are broad domain general frameworks, essentially, grand theories of mind implemented as computational models. They aim to explain all aspects of human cognition, problem solving, learning, memory, attention within a single coherent system. Two giants in this field, Soar and ACT-R, are both fundamentally based on production systems, but take different angles.
Let's start with SOAR, state, operator, and result. From Newell, Laird, Rosenblum, direct descendants of that original PSSH thinking. Sounds ambitious.
Hugely ambitious. SOAR aims to be a unified theory of cognition. Its core idea. All goal directed intelligent activity is basically a search through a problem space.
Like finding your way through a maze. Start state, apply operators, move left, turn right, reach goal state.
Precisely. SOAR runs on a continuous decision cycle. Rules fire in parallel to propose and evaluate possible operators for the current situation. A decision procedure picks the best one, applies it, you reach a new state, cycle repeats.
But the really clever, really human like part is how it handles getting stuck, right? Impasses and subgoaling. This sounds like how we figure things out when we don't know the next step.
It's a key insight, yes. An impasse happens when SOAR hits a knowledge gap. Maybe no operator gets proposed, or there's a tie it can't resolve. It doesn't know what to do next.
Okay, it's stuck.
And here's the magic. When SOAR hits an impasse, it automatically creates a substate. This is basically a new nested problem space with the specific goal of resolving that impasse.
So it sets itself a subproblem. Figure out how to get unstuck.
Exactly. This mechanism, universal subgoaling, allows complex reasoning like planning, breaking down big problems, even thinking about its own thinking, metacognition, to emerge naturally from the system, trying to overcome its own limitations.
Ah.
It doesn't have to be explicitly programmed, it's inherent in how it handles being stuck.
That's really elegant.
Yeah.
And this leads directly to how SOAR learns through something called chunking.
Yes, chunking is SOAR's main learning mechanism, tied directly to resolving impasses. When SOAR successfully figures out how to resolve an impasse within a substate, finds the missing knowledge, makes progress, it automatically builds a new production rule, a chunk.
What does this chunk represent?
It summarizes the situation, the conditions that led to the impasse and the successful action, the result that resolved it. This new rule gets added permanently to its production memory.
So the next time it hits a similar situation, bang, the chunk rule fires.
Exactly. It now has the knowledge it lacked before. It doesn't hit the impasse, it just applies the learned solution directly. Slow, deliberate problem solving, searching the substate, gets transformed into a fast, automatic skill, firing the chunk rule.
Wow. That computationally models the power law of practice, how we get faster at things with experience, turning knowing that into knowing how.
Precisely. It's a powerful model of human skill acquisition emerging from basic problem solving principles.
Incredible. Okay, what about the other big one, ACT-R? Adaptive control of thought rational. How does it differ from SOAR's approach?
ACT-R from John R. Anderson and his group also uses production systems, but its main goal is different. It aims to make detailed, quantitative predictions about human behavior. Things like predicting exact reaction times in milliseconds, error rates, memory recall patterns, and psychology experiments.
So SOAR is about the logical structure of intelligence emerging, while ACT-R is about the statistical, noisy, time-based reality of human cognition, predicting the measurable details.
That's a great way to capture the distinction. ACT-R is a hybrid architecture. It has symbolic production rules for procedural knowledge, the how-to, but these operate alongside underlying mathematical equations that model cognitive limits, memory processes, attention, etc. It has distinct modules like declarative memory for facts, chunks, and procedural memory for rules, mapping closely to psychological theories.
And it's especially known for its model of memory retrieval, how we remember, forget, have those tip of the tongue moments.
Yes, its declarative memory model is very sophisticated. Each chunk of information, a fact, a concept, has a numerical activation level. This determines how easily and quickly it can be pulled from memory.
What determines the activation?
Two main things. One, base level activation reflects how often and how recently you've used that chunk. Use it a lot or recently. Higher activation, easier recall. Crucially, this activation decays over time if unused. That's ACT-R's model of forgetting. 2. Spreading activation. Your current context, what you're thinking about right now, gives a boost to related chunks. Thinking about beach, chunks for sand, oceans, sunscreen get activated.
Makes sense. Things fade, but context primes related memories.
Exactly. And retrieval isn't guaranteed, it's stochastic probabilistic. The chance of retrieving a chunk depends on its total activation. If activation is too low, retrieval might fail. That's your tip of the tongue moment. You know it's in there, but the activation isn't high enough to retrieve it reliably.
And retrieval speed depends on activation too.
Inversely, higher activation means faster recall. This whole system allows ACT-R to make incredibly precise predictions about human cognitive performance, making it a vital tool in cognitive science research.
So granular. It models the messy, probabilistic, adaptive nature of our own minds. Amazing that production systems provide the framework for both Soar's logic and ACT-R statistics.
It really shows the power and flexibility of the core idea modeling thought as rule-based processing, from fixing cars to modeling human memory.
Wow, what a journey. This deep dive has really taken us from the philosophical roots of AI to the practical engineering, right up to modern hybrids and even models of the human mind. It's crystal clear that production systems are way more than just a historical curiosity.
Absolutely not. They're a fundamental, enduring paradigm for thinking about intelligence.
Yeah.
Built on that intuitive if then logic, they literally embody a computational theory of mind, the PSSH, mirroring cognitive elements like working memory, long term knowledge, attention. They offer a transparent logic that reflects how we often tackle problems.
And they delivered. Expert systems like DENDRAL and MYCIN showed real world value. Algorithms like Rete made them efficient. Shells like CLIPS made them accessible. But importantly, there are limitations that knowledge bottleneck, the brittleness, and those deep philosophical challenges like the Chinese room. They didn't just kill the idea, they actually spurred AI's evolution, pushed research towards connectionism and other avenues.
Right. And ironically, those perceived weaknesses, their explicit structure, their transparency, are now their greatest strengths in the modern era. They're the key to solving the black box problem of deep learning. They're being reborn in neurosymbolic hybrids, providing the essential layer for explainable AI, for building trust. They give us the why.
It underlines the enduring need for rules in AI. Maybe not always hand coded rules like in the old days, now they can be learned from data, but the need for structured, verifiable, explainable reasoning. That hasn't gone away. Rules provide that symbolic conscience, that clarity for powerful but opaque models.
And in a world just saturated with AI, understanding these rules, explicit or implicit, learn or designed it empowers you, the listener, not just to be a passive user, but to critically engage with these systems, maybe even help shape how they're built and used.
So, maybe the final thought for everyone listening is this: as you encounter AI, from your smart assistant to complex systems at work, try asking yourself, what are the underlying if thens here? What rules are governing its behavior? Or maybe more importantly, what rules should be governing it to make it more transparent, more reliable, more aligned with what we consider truly intelligent and trustworthy? This dive into production systems gives you that foundational lens to start asking those crucial questions.
All right, this is Military Industrial Museum. I'm signing off. I'll try to put more of these out. But thanks for listening. And you can go back. I'll save the recording and go back and review it.